Okay, so in this video, I would like to find the Galois group of the polynomial x to the fourth minus 2. So this is a polynomial that I looked at in a previous video, and we actually found that the splitting field of this polynomial over Q is Q adjoin fourth root of 2i. Okay, so I'll include a link to the video where I proved this. But now we want to find the Galois group. So that's going to be the group of automorphisms on this field. And it's going to be the automorphisms that preserve the base field. So basically it's going to be like automorphisms from Q adjoin fourth root of 2i to Q adjoin fourth root of 2i, and such that everything in the base field, which is Q, stays where it is, or is fixed. Okay, and we're going to use a couple tools to figure out what the Galois group is. One thing that we're going to use is we're going to use part of the fundamental theorem of Galois theory, and specifically we're going to use that the degree of our splitting field is equal to the order of the Galois group. Okay, so if you have a polynomial, like this polynomial is x to the fourth minus 2, the splitting field is going to be an extension of Q, and whatever the degree of this is equal to the order of the Galois group. So we're going to use that. And then the other thing that we're going to use is the Galois group of a polynomial, and assume that the degree of the polynomial is equal to some n. So the Galois group of f is a subgroup of Sn. Okay, so this is the symmetric group on n elements. The reason that the Galois group is a subgroup of this is to do with how the automorphisms permute the roots of the polynomial. So if you have an automorphism, it switches the roots of the polynomial around. And that switching is an action which is similar to a cycle in the symmetric group. Okay, so those are all of the tools we're going to use. So our question is, what is the degree of the splitting field, right? Because we have Q adjoin fourth root of 2i. And we can view this as Q adjoin fourth root of 2 adjoin I. Or we can view it as Q adjoin I adjoin fourth root of 2. Either way. And the total degree of this extension is going to be the product of the degrees of these two extensions. So we want the degree of Q adjoin fourth root of 2, and then we want the degree of Q adjoin fourth root of 2 adjoin I. And the product of those is going to be our total degree. So we want to know what's the degree of Q adjoin fourth root of 2, degree of this over Q. But this is just equal to the degree of the minimal polynomial. So one way you can denote that is like this. right? It's the minimal polynomial of fourth root of 2. And we know that that's x to the fourth minus 2. Okay, so the degree of this extension is actually 4. So we know that if we go from q up to q adjoin fourth root of 2, the degree of just that extension is 4. So I'll write 4. And then, so that's that degree. And then we just need to know the degree of q adjoin fourth root of 2 adjoin I on top of that. So let's come down here. So we need to know, we're trying to find the degree of q adjoin fourth root of 2 adjoin I over q adjoin fourth root of 2. But then that's just going to be the degree of the minimal polynomial. This time it's going to be the minimal polynomial of I. And it's going to be the minimal polynomial over q adjoin fourth root of 2. Okay, and notice that this field doesn't have any complex numbers, right? So if we take the polynomial x squared plus 1, for example, this is a polynomial that has I as a root, and actually it only has complex roots. So this is clearly going to be an irreducible polynomial over q adjoin fourth root of 2, so that tells us that this is the minimal polynomial of I. Okay, so this is our minimal polynomial. It's a degree 2 polynomial, and so that tells us that the degree of this extension is 2. So that's 2. Okay, so now we know that the degrees of the two smaller extensions are equal to 4 and equal to 2. So the degree of q adjoin fourth root of 2 I over q is equal to 4 times 2, or 8. Okay, and this is really important because if we go back to our fundamental theorem of Galois theory, right, this is one of the tools that we wanted to use, the degree of the field extension is equal to the order of the Galois group G. Okay, so that tells us that this is the order of G. So we're closer to finding out what the Galois group is. The next thing we want to do is we want to notice that we started with a degree 4 polynomial. So this is a degree 4 polynomial. And recall, one of the other tools I wanted to use was that the Galois group is a subgroup of Sn, right, where this n is the degree of the polynomial. But because this is a degree 4 polynomial, that tells us that the Galois group has to be a subgroup of S4. So we're putting all of this together. We have our Galois group G. Whatever it is, it's a group with 8 elements. And, okay, so it has 8 elements. And then it's a subgroup of S4. Okay, so now we just want to ask, let's come down here a little bit, what are the 8 element subgroups of S4? And I won't get too much into this for time reasons, but there are certain things that we know about 8 element subgroups of S4. Specifically, we have the Sylow theorems. And using the Sylow theorems, you can prove that every 8 element subgroup of S4 is isomorphic. Okay, so if I have any 2 subgroups of S4 that have 8 elements, they have to be isomorphic to each other. This is to do with 8-element subgroups being what are called maximal 2 subgroups. So I'll post a link to an article where that's explained in more detail. But basically every 8-element subgroup of S4 is isomorphic, so it's enough to show, or it's enough to find basically a single 8-element subgroup of S4. Okay, because if I find one 8-element subgroup of S4, all of the other 8-element subgroups will be isomorphic to that. So whatever my G is, it's an 8-element subgroup of S4, and whatever 8-element subgroup of S4 I find is going to be equal to G. So I'm going to claim, you can check this, that D8, okay, so this is the dihedral group, and you can think of this as like D2N. It's a lot of group theory that's needed to do these exercises, but this is basically the automorphism group on a polygon with n sides. Okay, so this is the symmetry group of a square, and flipping and rotating the square. But I claim that, you know, this is actually a subgroup of S4, which you can check. And so that proves that G is actually equal to D8. So finally, we conclude that, you know, D8 is the Galois group. You can also denote it as D4. So sometimes people will write this as D4, depending on your preference. But so this is the Galois group of x to the 4th minus 2. And we get that using fundamental theorem of Galois theory, and then also using the CLAV theorems. So that is going to be it. Thank you very much for watching.